Namaste. This is Nataraj again. Um, Today, I'm going to discuss an interesting topic: modified Newtonian law. Right? So, in the previous class, we had a discussion on Newton's sine squared law for the pressure coefficient, and we have made a derivation, and we finally arrived to the coefficient of pressure Cp, that is equal to 2 sine square theta. And it has a good application in, say, if you consider the flow over an short body, say when there is a formation of oblique shock, inside the thin shock layer, you can see the flow, right, which we have assumed in the flat plate of the Newtonian law, right? So it is like almost like, the based on the Newtonian model, where the stream of particles in a rectilinear motion, and it is almost like a pellets from the shotgun blast, and then it is striking on the surface, and it would lose all its momentum normal to the surface, but it would move tangentially, almost parallel to the surface, right? So that is what our discussion in the Newtonian law, and now we will discuss about the modified Newtonian law, right? So modified Newtonian law is also one of the approximate methods we use in the hypersonic flow theory, right? So, okay, I acknowledge the hypersonic and high temperature gas dynamics by John D. Anderson, right? So then, so in the local surface inclination methods, if you see, there are many methods. Say, for example, in the Newtonian flow, so we have initially considered the Newtonian flow, where we have already discussed the sine square law. So now we will discuss the modified Newtonian law, and then we will do the centrifugal corrections and the further accuracy considerations and applications. Right? Then in the same local surface inclination method, we will further go to the tangent wedge method, tangent cone method, and the shock expansion in the later stage. Right? Okay, now what is modified Newtonian law? Right? I recommend you to see the references later, but I will just go through the what the Lesterlies proposed. Right? So Lesterlies proposed an interesting method for the modification of the Newtonian theory. And you already know very well in the discussion when we have calculated the Cp, that was in the Newtonian theory or Newtonian sine square law, we write 2 sine square theta, right? So this is what our Cp in the Newtonian method. Now, Lesterlies proposed this particular method, where instead of that particular 2, he has considered Cp max. Right? So Cp max is the maximum pressure value, right? This is the maximum pressure value, right? Like it is evaluated in the stagnation point behind the normal shock. If you think a little, it will be necessarily something like a stagnation pressure of the hypersonic body, right? Okay, so let us say the coefficient of pressure, that is Cp max, which is considered, right? So we can write P naught 2 minus P infinity by of rho infinity V infinity square, right? So P naught 2 is a stagnation pressure, right? That is behind the normal shock, and P infinity is a free stream pressure, right? Now, okay, that is one is the total pressure and another one is static pressure, and half rho V square V infinity square rho infinity V infinity square is the dynamic pressure, right? Now, say now say we already know the normal shock theory, right? Normal shock wave theory. We have gone through the Rayleigh-Pitta tube formula, right? So Rayleigh-Pitta tube formula, which says that P naught 2 by P infinity is equal to gamma plus 1 the whole square into m infinity square by 4 gamma m infinity square minus 2 into gamma minus 1 the whole power gamma by gamma minus 1 into 1 minus gamma plus 2 gamma m infinity square by gamma plus 1, right? So this is actually, we have already derived in the compressible flow based on the normal shock theory, right? And this is called Rayleigh-Pitta tube formula. Now, let us say we already know, that is like we can write the of rho v square, right? Of rho infinity v infinity square, because we already know p naught 2 by p infinity, hence we go to the next point here, right? Of rho infinity v infinity square. So this of rho infinity v infinity square can be written as gamma p infinity m infinity square by 2, right? So this, I think you know very well, this v square, v infinity square, and then v infinity square by a square. We had a discussion like how to convert that. Right? I recommend you to go through the one which we have done before. Okay. Now let us say the CP max. Right? We already know the CP max. That is P naught 2. Here we have a here. So this is P naught 2 minus P infinity by of rho infinity V infinity square. Now let us consider this CP max. Right? Okay. So we can write the CP max here. CP max. Right? We can write the CP max is equal to 2 by gamma m infinity square into P naught 2 by P infinity minus 1. Right? I hope you understand how we arrived to this point, because this one we can write this as P infinity into P naught 2 by P infinity minus 1 by of rho infinity V infinity square. So here you have a V infinity again, I mean P infinity again, right? So we can cancel it, and finally we can arrive to this particular formula. So this is what the P naught 2 by P infinity in CP max, correct? So now you can substitute this P naught 2 by P infinity in CP max. Okay. So let us write in that way, right? So let us say CP max, right? Let us combine the equation. So when we combine the equation, we can write CP max, that is equal to 2 by gamma m infinity square, right? That is multiplied by gamma plus 1 into gamma plus 1 square into infinity square divided by 4 gamma n infinity square minus 2 into gamma minus 1, right? The whole power gamma by gamma minus 1. Minus 1 into 1 minus gamma plus 2 gamma m infinity square divided by gamma plus 1 minus 1. Right? So we write this equation by combining these two equations, right? This Cp max, where we substituted this particular T naught 2 by T infinity here, right? So we can write this and this. Now we have this equation, right? So as usual we do, right? Like we consider the limit here, right? Now let us consider the limit. Say the limit which is tends to m, I mean m tends to infinity, right? So when we consider m tends to infinity, right? So we can reduce this equation to a certain extent where say this m tends to infinity. If we make m tends to infinity, so this is not necessarily we need to consider, right? Then if n tends to infinity here, probably this term also need not to be considered. And okay, then it will become like this will be like this. Right? This will go away, and this also will go away. And okay, then you multiply m infinity square here and m infinity square here also go away, and here you have a gamma, and here you have another gamma. Okay. So by considering the m infinity tends to infinity, then we can write this equation as say Cp max that is equal to right. So we can write the Cp max as this 2 and the here you have 2 and here you have another 2. So okay, let me write the gamma plus 1 the whole square, right, by 4 gamma 4 gamma the whole power gamma by gamma minus 1, and that is multiplied by 4 by gamma plus 1. Okay. So Cp max becomes Cp max is equal to this particular value, right? Cp max is equal to gamma plus 1 the whole square by 4 gamma the whole power gamma by gamma minus 1 into 4 by gamma plus 1. Now, okay, so we already know gamma, right? What is gamma? You have a Cp by Cv and whatever it is, and let us write gamma is equal to 1.4. Now, Cp max is a function of gamma only now. So when we consider gamma is equal to 1.4, then what is Cp max? Cp max is equal to, so please do the calculation. So here you see the Cp max, it will become like 1.83 or so. Now let me say the gamma that is equal to 1. Let us assume gamma equal to 1. then what will happen? So when you say gamma is equal to 1, then this equation Cp max, that will be reduced to 2. Do you remember what is this 2? The Cp max 2, if you substitute the Cp max 2 here in this equation, then it will become the Newtonian proposal of the sine square law, right? So here Cp max is equal to 2 when you consider gamma is equal to 1. Okay. Well, so we have modified Newtonian law, which discusses the final Cp, that Cp is equal to Cp max sine square theta. Cp is equal to Cp max sine square theta, and you have a Cp max here in terms of gamma. Okay. So let us draw and let us plot the graph, right? We have a graph between, say, m infinity, because you see the Cp max is no longer independent of Mach number, right? So here in this equation of Cp max, you can see the m infinity and various m, right? So the effect of finite Mach number is there on Cp. Okay, so the Cp max will be dependent upon the finite Mach number. And as usual, we know if m infinity tends to infinity, correct? That is the assumption here. If m infinity tends to infinity and the gamma is 1, then the Cp max yields the traditional Newtonian sine square coefficient of pressure, right? That also we have identified. So let us see this particular graph, right? Okay. So let us see this. We have a modified Newtonian law, and we have a Cp max here, right? So, and m infinity, and it is plotted for various Mach number and the gamma. So you can see 1.66, 1.4, and 1.2 and 1, right? So when gamma is equal to 1 and m tends to infinity, it will become 2, right? Maybe approximately equal to 2. Okay. So that is what our finding, right? And the 2 points we need to remember. One is modified Newtonian law, which calculates the Cp max, which is dependent upon the Mach number m infinity, and we have seen the graph, right? Cp max with respect to, so Cp max, m infinity, gamma, and so on. Second point, if we consider m infinity tends to infinity and the gamma tends to 1, ultimately the Cp max becomes 2. That in turn represents the Cp is equal to 2 sine square theta, which is necessarily the Newtonian sine square, right? Newtonian sine square coefficient of pressure, right? This becomes Newtonian. Okay. Now, so now we can predict the Cp at some point probably, and then say here it is, so we can predict the values, say the pressure ratio, and it is plotted here. This is plotted for Mach number m infinity is equal to m infinity is equal to 8, right? And P02 is actually the pressure, right? You know the stagnation pressure or the total pressure, and the P02 by P, when we calculate for the various location, this is the y and this is b in the direction of Mach number m infinity, right? So the profile is drawn based on the b is equal to 0.769 y square minus 1. Here you see the results of the exact time option results and the modified Newtonian and the straight Newtonian. You know the straight Newtonian is 2 sin square theta, and modified Newtonian is Cp max sin square theta. Okay, so um, so that is what the solution is. So we can say from this that the modified Newtonian predicts the Cp better when compared to the straight Newtonian for such blunt bodies, right? Say such blunt bodies, modified Newtonian predicts very well. So here we can say that uh, the dashed line, which is the straight Newtonian result, it lies 9% above, right? 9% above the exact result by considering the average point, right? So it is almost like, we had a discussion in the first that the P02 is actually the pressure, the total pressure measured behind the normal shock, and which can be necessarily considered as a stagnation point of the given body, right? So, okay, so this forces the Newtonian theory to be exact at the stagnation point where we have a value of Cp max equal to 2, right? And the variation of Cp, right, away from the stagnation point, which follows the sine square behavior, right? So sine square theta and Cp 2 sine square theta and Cp max sine square theta both follow the similar trend, right? But for the case of blunt body or blunt body, the modified Newtonian predicts better, right? So we have studied two methods. One is Newtonian method and another one is modified Newtonian method for the calculation of coefficient of pressure, right? I stop at this point, right? Um, Thank you very much. And we will look into the centrifugal force of the fluid particle in the next class. Okay. Thank you very much.